Let me just share the screen in full screen mode. Yeah, so I hope the screen is visible and I'm audible. So today will be the third week for our Electrical Machines 2 NPTEL program. From this week, we will be entering into uh, deeper concepts in electrical machines. That we will first start with the winding formation in a machine, how the windings are being wound, and what are all the terminology related to windings. Actually, this winding concept in electrical machines is pretty interesting, and it's the way the coils are being wound, the reason behind why they are wound in such a way. That is kind of a really interesting concept, I would say. So yeah, we will take it very slow, like how the windings have been bound and what is the terminology related to those, which will be very important in understanding the winding schemes. So you might have come across some standard terms related to the winding, like slot pitch and pitch factor, distribution factor, coil span, phase spread, etc. So these are all terms. If you clearly know what they actually mean, what they actually relate to, it will be very easy to understand the windings. So in that way only, we will start introducing one term at a time, and I hope you will all get a clear picture in understanding them. So you might have heard like when we wound a winding in a machine, usually people talk about two kinds of windings. Can anyone tell me what are the two kinds of windings people usually wound the windings in a machine? They are distributed winding or a concentrated kind of winding. Now there are two kinds of windings which is usually preferred. Like out of these two windings, each winding has its own advantages and also disadvantages. But for many reasons, like concentrated winding isn't wanted that much. Like there are good reasons behind it. Like the name itself says the windings are being concentrated in a particular slot of a machine. Like if you are like concentrating many number of turns and you're accommodating it in only one pair of slots, so that makes the rest of the rest of the machine underutilized. So yeah, that is one disadvantage regarding the concentrator winding. And one more disadvantage of the concentrator winding is so when you keep lot of coils in a slot, uh, you can't keep after some amount of time. There should be some restriction on maximum number of turns that you can put it in a slot. So it's not always easy to put lot of coils in a concentrated slot. And also we just discussed that we should not make the entire machine underutilized. So for these reasons, we have to go for a distributed kind of coil winding. Now, distributed means, let's say we have X turns and in X coils, so we want to distribute it and we have to spread across the machine. But even distributed kind of winding will have some disadvantages over this concentrated winding. So that we will actually see today with good derivations and examples, and you will can clearly understand why it is what is the disadvantage related to the distributed winding. So the main disadvantage for the distributed winding is the kind of voltage output you would get. Like let's say you have three coils and you have placed in a concentrated manner in a machine. So the resultant voltage you would get in a concentrated winding will always be greater than compared to the resultant voltage you would get in a distributed winding. So that we will see it even more clearer. You will get a good picture, but I'm just saying it in advance what we are going to discuss now. Now the that actually after this discussion you can easily relate to two couple of factors that are distribution factor and also pitch factor. So that actually defines why there is a difference in the voltage if it's a distributed winding, and why maximum voltage we will get in a concentrated winding. So that's how we will start our discussion today. And we will start our discussion with a distributed kind of winding, and we will see the resultant voltage in the distributed kind of winding, and we will see the resultant voltage in the concentrated winding, and we can easily spot the difference in the voltages which we get in the distributed and concentrated type of winding. Now, let's say we have 30, let's say three coils. Let's say we have to distribute the coils, and okay, let's say we have three coils we have, and we have 30 turns. For example, I'm saying three coils, total we have 30 turns. Now, if you see how many like if you want to distribute these three coils in 30 turns, what we will use is it's like, okay, in coil 1 I will keep 10 turns, and coil 2 I will keep 10 turns, and coil 3 I will keep it 10 turns. That's a distribution kind of finding, not concentrating all the 30 turns in single slot, but we are spreading over it, and we are keeping it at each 10 turns per each coil. Now, when we keep it like that, I'm just going to draw, let's say, um, just one and one dash. And it's one means the going end, and one dash is the return path. So I'm just placing these two one dash in this fashion so that you can know we are going, we are taking the coil inside through one and taking it back through the one dash, and that is one coil. And we have another, let's say it is two dash, same thing, and another three dash. Okay, so why I'm showing it like this: one dash, two dash, and three dash is like, let's say we have three coils and we are trying to put it like that: one, two dash, three dash. Okay, now we are trying to distribute our 30 turns in these three slots. Like now, when we now we have three distributed windings and three distributed, um, uh, 30 turns we have distributed in three coils. That's okay. Now, when we do it like that, it will give rise to three different voltages, because all these three are under same magnetic field, and the kind of voltage they will generate will be equal in magnitude. That is, I'm writing it here. One dash will corresponds to some voltage. I'm calling it as E11 dash, and two dash will correspond to a two dash voltage, and three dash will result in a E33 dash. Now this is, I placed these coils in a distributed fashion. Now when we are placed all these coils in a distributed manner, now what I am trying to do, I'm trying to calculate the resultant of these three voltages. Now, the important thing is, since it's a distributed, there will be some like angular displacement between these two coils. Now, in the figure, you can easily see this is coil 1 axis. I'm just, and this is coil 2 axis, coil 3 axis. Okay. Now, there is a clear angle visible between these two slots. You can see now between 1 and 2 dash there is a angle. Now each between 1 and 3 there is an angle, there is 1 to 3 there is an angle. Now between these are not clearly equally placed, but in actual this will be equally spaced. The angle between any two slots we call it as a beta, which is a slot pitch. Now, when I say beta, it's always how the slots have been arranged across the 360-degree plane and how much is the angle between these two. Now that is called we call beta, but beta it should be electrical. That's what we need. When we say in 360-degree plane, the angle between slots it's in mechanical, and how we will convert it into electrical by multiplying it with the pole pair. That we will see calculations in the subsequent discussion. But I'm just giving you a introduction that beta is what the angle between two slots, slot pitch. Now I'm trying to calculate the resultant voltage. Now, before going into this distributed kind of resultant voltage, I'll just show you how it will be for a concentrated, because once you understand concentrated, it will be easy to relate. As I said earlier, for a concentrated winding, there is no dividing these turns into multiple slots. Now we are placing all the voltages into single slot. That is what we call it as a co-phasor, because all the voltages are placed in single. There is no displacement, there is no angular displacement. All are having same magnitude, same length, and also there is no phase displacement between these two. Like let's say if this is E11 dash phasor, it started here and it is like this. Now E22 also will have having same magnitude and same phase. These two are of same length also. In similar way, this is E33 dash, which is having same length, magnitude, and also phase as the rest of the two voltage phasors. So this is called we call this kind of arrangement as a co-phasors. They are having same phase, also same magnitude and same length. Now you see, if I want to measure the resultant, it's nothing but from here to here. That is the resultant here. Since it's a cophasor, calculation of resultant will be pretty easy. It's just an algebraic sum of these three. Now, E resultant in concentrated winding. Algebraic sum because all are in same phase. E11, E2 dash plus E33 dash. Since all are of equal magnitude, I can write it as 3E, which where E is equals to E11 is equals to E22 plus E33 dash. Now, this is what we get. Now, this is the maximum voltage you could have got from three windings possible, from these three coils possible. Now, we will see how this will be in a distributed kind of winding. The question is, if we connect three coils in a concentrated and then the distributed manner, what is the ratio of their resultant voltages? That's the point of interest we have. Now, clearly we saw in the concentrated winding, the equivalent resultant voltage is 3 times the individual voltage, which is because of the cophasor placement. Now, if it's in distributed, it will definitely be less than concentrated, as we discussed earlier. Now, what factor it is reduced? Now, if we can calculate the ratio between these two voltages, it's nothing but the distribution factor. So that's how the distribution factor came into picture. That's what the actual meaning of a distribution factor. So that's the question. And if we take the ratio of their voltages, we can easily get the distribution factor. Now we saw if the coils are in concentrated winding, this is the resultant. Now let me just the case B. Now when coils are distributed. So when I say the coils are distributed, the uh, of course these coils are series connected. I just placed it in different slots. This is how the connections are being made. I'm just showing the overall circuit. 1 1 dash, and then we have 2 2 dash. and 3 dash, and there is some plus minus voltage here, plus minus voltage here, plus minus voltage here. I'm trying to calculate the total voltage, but this is not a algebraic summation of voltages etc, but I have placed it in a slots. There is some kind of displacement between all these uh, voltages which we can see here. This is not simply a algebraic summation of voltages. Now when I am placing these coils in the successive slots, I can see there is an angle between any two consecutive slots. That's what we saw it as a beta. But beta should be always be, we need to take it in the electrical manner. Now, beta electrical is what? The angle between two consecutive slots. So beta electrical, like for example, if I say, now let's say we have 36 slots. Now if I'm trying to calculate the beta in it. Now I have 36 slots. I need to spread that 36 across the 360 degree of the machine. And now this is 360 degree. Now I need to place 36, 36 like that. I have placed so on. And entire 360, if I need to allocate for 36 slots. So each angle between consecutive slots should be definitely 10 degrees. So but we are seeing it in a mechanical plane. That is actual mechanical degree which we can see, but in the electrical form this is beta, this is also beta, but it is beta mechanical. You need to understand, if you calculate beta electrical, it will be beta mechanical into pole pair. You need to understand how many poles are there, and you divide it with the two, then you get the pole pairs, and multiply the beta mechanical with the pole pairs to get the beta electrical. So that's what I meant when I talk about the slot pitch, the angle between any two consecutive slots. It's a beta. Now here, let's get back to our circuit, and I'm trying to calculate the magnitude of induced RMS voltage. This is total resultant magnitude, but if you see the magnitude of induced RMS voltage in each coil, that will be same. In each coil will be same. That is just as before in the concentrated or in the distributed. The in each coil the magnitude of induced RMS will be same. The magnitude, I'm saying E11 dash is equals to E22 dash phasor is equals to E. That will be same. Now the resultant won't be same because in this distribution definitely the angle factor comes into picture. Now for that we will see it in a very neat phasor diagram, and then we will solve for it. And let me just see here itself. Let's first see this in a very basic structure. Now let's say if I have 1 1 dash winding, I will take 1 1 dash here like that. I have placed my 1 1 dash phasor here because I'm drawing it here because we can see this concentrated winding figure here. I have drawn E11 dash. Okay, now this is 1 1 dash. Now to place one E22 dash, I can't place it here. They are not in cophasors anymore. There is an angular displacement of beta between each coil. Now if this is the plane and if this is beta, I need to place my E22 here. E22 dash, this is E11 phasor here and E22 phasor here. But however, the magnitude of induced RMS voltage in each coil will be same. So that's same here. And now E33 dash will be beta from E22 dash. If this is E2 dash plane, then at an angle of beta, E33 dash will be. And again, this length would be same. Now what I am interested is calculating this resultant. From this point, I can say E13 dash, right? This is the resultant. Now, now you can easily relate that it's not just algebraic sum, but there is a angular factor coming. Now, with a good phasor diagram, now we will see how mathematically we can calculate this resultant, and then we will get a picture of what is the total resultant voltage in a distributed kind of finding. So that's what I will try to make here. Let's see if I can place it here. Okay, I'll try. I'm trying to draw the same phasor, but I took the E11 dash here. This is the point A, and this is the point, you can say it's B. And from here, at, at I'm taking this as a beta, and this is E22 dash, and this is a beta, this will be E33 dash. Okay. Now, the magnitudes, as I said, they are same. Now, what will be the resultant? That is E13 dash, this part. A, B, if I call this B, if I call this C, and if I call this D, I'm interested in the AD, which is E13. I'm drawing it here. E13 dash, which is the resultant. Now, I would like to calculate E13 dash here. Now, if you see these three phasors and the resultant, you can see all the sides are equal, and it's look now it is looking like a polygon of equal sides. All the three exterior, not the resultant, of course. Resultant is bigger, but the three sides are looking like a polygon of equal sides. Now, when it's equal sides polygon, I can circumscribe these sides with a circle. So that's what I'll try to do now. Let me just erase this. This is B. Okay, E22, this is E33 dash, and this is the circumscribed cycle. So that's how the circle would come around the joint, around the edges A, B, C, D. And now, with some simple mathematical transformations and some mathematical representations, you can easily calculate the result. That's not a difficult thing. Now, this is the beta, and this is again beta. And if I try to locate the center of the circle, now this is the circle, and somehow it will be like around here, maybe somewhere around here. That is the center O. Now I am trying to join all the edges from the center. This one to that will be the radius of the circle. 0D, 0C, OB, and OA. All these are the radius of the circles. This will be R. Okay. Now this particular beta here, this is beta, and radius is equal. All the radiuses are of same size. Then this, according to mathematical property, this angle will also be beta. Now all the angles you can see between all the radius will be equal to beta. This is beta, and this will also be beta angle. Okay. Now let's start calculating the resultant. Now from the O center, I will try to draw a perpendicular onto the my resultant which I want to calculate it. Now I will mark this point as M. I have drawn a perpendicular OM. Now let R be the radius of the circle and OM be the perpendicular. Now I want to calculate this entire resultant in terms of R. So that will be pretty easy. Now if you see here, I guess what is this? Okay. From triangle A, okay, AOM or AOM. Now you see this particular triangle. This particular triangle, if you see AOM, this particular, this is beta and this is beta. So this will be beta by 2. This angle and this angle, beta. Now angle AOM will be beta plus beta by 2, 3 beta by 2. I'm just trying to calculate my resultant in terms of radius r. So I'm trying to get the hypotenuse. We know the hypotenuse r and also this particular side. So then I can get the resultant here angle. Now from the triangle AOM, if you see, I know the hypotenuse radius, that is r, and I know the angle. This is 3 beta by 2. Now from the sine property, you can calculate the AM part. AM will be sine theta is equals to what? Opposite side by hypotenuse. Now opposite side will be AM, hypotenuse will be R, where the angle is 3 beta by 2. Now if you use the mathematical property, AM will be R sine 3 beta by 2. So this is AM. We already got the half of the resultant, right? Now it's just the midpoint of resultant M. Now if this is AM, which is R sine 3 beta by 2, and this will be also equal to R sine 3 beta by 2. Now total resultant will be E13 dash magnitude will be 2 times of R sine 3 beta by 2. I hope this is understandable for you. It's not just a difficult, just a simple mathematical formula. Like that is in equal sides. If you know the exterior angle beta, then it will be the equal to this interior beta as well. From that beta, we calculated the resultant as in terms of radius. We got the half of radius as 3 r sine 3 beta by 2, and the total resultant will be 2 r sine 3 beta by 2. Still, we didn't calculate the complete method yet. Like it's still in the radius. We don't know the value of radius. R is still unknown. We will see later how we can solve this one. But now we got an expression for resultant in terms of radius. That is 2r sine 3 beta by 2. Now, when coils are concentrated, what we got the equivalent, that is 3e. That is simple. Now, what we got 2r sine 3 beta by 2. Like now, let's see the comparison. When coils are concentrated, I mean all the all the turns I have just placed like this. Like if this is 1 and this is 1 1 dash, and all are placed in this manner. So all are concentrated. There is no distribution, and everything is in co-phasor. All are like this. Now in that fashion, what I got the resultant E11 dash, E22 dash, E33 dash. Now E13 dash is equals to 3 times of E, that is in the concentrated winding. Now let's take the ratio. The ratio what I am trying to take is resultant voltage when coils are distributed. Now I'm trying to find the factor by which the voltage is being reduced. Now the denominator will be same, the resultant voltage when coils are concentrated. So now what is the numerator here? What is the resultant voltage we got when it is distributed? In the previous slide it is 2R sine 3 beta by 2. 2R sine 3 beta by 2. And the denominator, the resultant voltage when it is coils are concentrated. So it is nothing but 3E, right? It's direct algebraic sum. Now, what we are calling this ratio, as I said before, this ratio is nothing but the how it is distributed, right? Distribution factor. That we calling it as a distributing factor. And we are denoting this with the K with a subscript of D, which is KD. Now we got the KD, but KD is in terms of R, because I can calculate beta, I can calculate resultant voltage. That is what we want to calculate. But R is something which we don't know. Now, what could be the value of R? Now again, we will go back to our phasor diagram, and then we try to get the value of R somehow in terms of known quantities. Okay. Now let's go back to our phasor, and here if you see, I am trying to look at the this particular triangle O and D, like this particular OCD. I am taking this particular triangle. Before that, as before I have drawn the perpendicular OM, I am trying to drop another perpendicular from here to the, I'm calling it as OM. This is a perpendicular OM. Okay. Now, if you see this triangle O and D, what is the angle at this particular O, NOD? Angle NOD. If you look at the angle at O, this is entirely it is beta, and this will be beta by 2, right? Angle NOD is beta by 2. That's simple. It's just perpendicular, it will make the angle half. But from angle OND, triangle OND, we know the hypotenuse is R and this angle is beta by 2. Then definitely you can calculate the opposite side, which is nothing but the ND, right? OD is R and angle O is beta by 2, and ND we can calculate. OD is equals to R and angle NOD is beta by 2. This gives ND, which is ND is nothing but this particular side ND. ND is equals to R sine beta by 2. Now, if it is ND, and what is CD? This will be 2 times of ND, right? CD is equals to 2 times of ND, 2R sine beta by 2. Now, what is the reason behind calculating CD? because CD is nothing but our E. CD is nothing but E33 dash, right? E33 dash is, we know the magnitude of this E33 dash phasor, it's nothing but E. Now, we got the radius in terms of some voltage we got. Now we got CD, which is nothing but E. Now we got radius in terms of E. Now I can write E is equals to 2R sine beta by 2. Now if you substitute, we are trying to find R, and we got R is equals to E by 2 sine beta by 2. Now let's substitute this value of R in the distribution factor formula, and then we will get even more simplified formula for the KD. Now what we got KD before? 2R sine 3 beta by 2 divided by 3E. But we got E as 2R sine beta by 2. Now let's substitute here 2R sine 3 beta by 2 divided by 3 into E. I am substituting it as 2R sine beta by 2. Okay. Now this 2R gets cancelled, and I am left with KD is equals to, okay. So this is the formula you might have come across in many problems in gate questions. They are trying to ask the calculate the KD if you have three slots per pole per phase and whatever for the n harmonics, etc., etc. This is the base formula we got. KD is equals to sine 3 beta by 2 by 3 sine beta by 2. Now, if this three we got because we started with three coils per entire machine. So, if there are m coils that are distributed, or if there are m slots per pole per phase, then we have to we will get that number in place of three. Now, if we are distributed three coils here, if m coils are distributed, now I'm just trying to generalize this formula. KD will be sine m beta by 2 3 sine, sorry, m sine beta by 2. So this is the standard formula for distribution factor. You also need to understand the formula here and remember you can remember it. But the ultimate relevance, what is the significance of KD, you should understand. Now, what this KD signifies is, now whenever you go for a distributed winding instead of concentrated winding, this is the factor by which your resultant voltage will be reduced. So that is a ratio. Like if let's say I got 10 volts in concentrated winding, in distributed winding I will get 10 multiplied by KD. This is sine m beta by 2 by m sine beta by 2 times the voltage you will get if it's a distributed winding. It's a concentrated winding. But if looking at this, you can say that my concentrated winding will always give more output voltage. But still, why people are going for distributed winding? We already discussed in the first part. The more coils you placed in a single slot, the less you are utilizing the machine. The machine will be left underutilized. And the more turns you are placing in a slot, the entire slot will be restricted. You can't place you can place only so many coils in a slot. So that will also make the congested winding very complex. So making it distributed will make the entire machine utilized, and also it will be spread across the machine. But the only down side is you will get a bit less voltage here. That is what we have seen here. So yeah, that is the factor by which you will get the voltage, and we are calling this factor as a KD distribution factor. Now M here will be the number of coils that are distributed, and usually people will also say the M as slots per pole per phase M. We will see that in the numericals which we will solve, and the beta here will be the angle between any two consecutive slots. So this is an important formula. You can note it down, and you can. It is very important for the numericals which we will solve, and not just this week, and but it is also important for gate uh, 1 mark questions, simple direct formula related questions. Now let's see the another important factor, that is the pitch factor. We denote pitch factor with a capital K or small k with a subscript P. Now, this is also another very relatable factor. Is just how we have related distribution to the machine's output voltage. Now we are also relating this Kp with a coil related to coil span, like how we are placing the coil in the windings. Like if we are placing a coil in one slot and we are placing the other end of the coil in another slot, how it is going to affect the voltage. Okay, that is what pitch factor. It's very simple, like it's very interesting and simple also. You don't have to worry about what is kp, what is kd, but if you understand the actual relevance of that kp and kd, it will be very easy to understand. Okay, now for any coil, say I have a coil, I am naming it as 1 dash, that is 1 is the going path and 1 dash is the coming path, and now I am trying to place that particular coil in a machine. So this is one, and okay, let's say it has more turns and all, whatever it is. It will come back here. So it is 1 dash. Now this part, this axis from here to here. So this is 1 and this is 0. I'm just calling it. And this is also 0 and this is 1 dash. Now this is what 1 0 is. I'm trying to place it under one pole. Now 0 1 dash will be coming back. It will be at the opposite pole. Let's say if it is under the south pole, let's say I'm placing 1 0 under the south pole, and it will go behind the winding, and it will come back from the north pole. So that's how ideally we should place that. Then only if we are placing one complete coil under opposite polarities with the equal strength, that's how we get the maximum voltage. That's the ideal way of placing a coil. So in other words, what I want to say is, like what we call this particular thing as a coil span. So this the coil has been spread over 180 degrees. So we know in a, if there is a two poles in a machine, 180 degrees will be for one pole and 180 degrees for the another pole. This is I'm again reminding you, it's not mechanical. This is electrical. 180 degrees electrical. Always two poles will have a 180 degrees electrical. This is electrical. Okay. In other words, I'm calling it as a coil span. Coil span will be 180-degree electrical. So this is what I'm talking about when it's 180-degree electrical. Now, for example, if you see a small example, let's say we have um, for each pole. So this is south pole, and under south pole I have uh, any random number like 6 slots. Okay, this means 6 slots per pole I have for south pole, and a north pole also I have 6 slots, that is slots per pole. Now if you see each coil, each coil will have this kind of spread here. Now what it signifies is, what this particular 6 slots signifies is, if coil side in slot 1, okay, these are 1 2 3 4 5 6 slots, and 1 2 3 4 5 6 slots. So I have placed 1 2 3 4, 5, 6. So these all six are under one pole, let's say south, and this 1, 2, 3, 4, 5, 6, all these are under north pole. Now, if I am placing one coil side in slot number 1, okay, I have placed this 0, 1, whatever you are seeing it here, I am placing it here, 1, 1, and the other side of this coil will go into the 7th slot. So there is a 6 slots between each pole. Now that's what I meant. The return coil side must be in the slot 7. This is slot 1 and this is slot 7. That's what I meant when I say it as a coil span is 180-degree electric. So one coil side is in slot 1 and another return coil side must be in the slot 7. So whatever part this behind part, this part is there, no? Like a triangle kind of. That is usually we call it as a overhang. So that is not a useful part because that does not come under any pole in the machine. It's just a base part, overhang. That's why people used to reduce that overhang part so that we can save the winding, copper winding and anything. So that's another discussion, but here you understand, right? If you are placing one coil slide in a one slot, after this coil span, or you can say after the slots per pole number, we will have the return slide. So now we have six slots, right? Uh, these six slots are spread across 180 degrees, right? Now each slot will take how much angle? Because six slots, 180, right? Now each slot will definitely take a 30 degree. So that's what we call it as a beta between each slot. Now that's how it is. 6 times 30 is equals to 180. Now it's very good. It is equally placed and everything is good. Now here the coil span is also 180 degree. Coil span is 180 degree electrical. Now comes the main discussion. So what if I place a coil not in the 7th slot? Maybe I will place it in 6th slot itself. Like I am not placing it in completely 7th slot. I am placing it in one slot before. So if I place like that, I placed one and I placed another one is this is 6th slot and this is 7th slot. So there I have lost 30 degree here, right? Now my coil span is 150 degree. It's not 180 degree. Now if I'm placing a coil such that I'm having a coil span of 150 degree, then whatever voltage we will get will be lesser than the before case. Because what we have discussed before, if we are placing a complete coil, each side of the coil under different poles with opposite polarity and with equal strength, then only we will get the maximum voltage output. But when I am placing my coil span with less than 180, here it is 150 degree, then the voltage we get will be less. How much it is less? By what factor the voltage will be less? So if we try to find that factor, it is called as pitch factor. So that's how we relate this pitch factor and distribution factor to the output voltages. Now see, why the name pitch? Pitch came in this pitch factor because it's slot pitch. Each slot is having some kind of 30 degree or 20 degree. Now we are reducing it. Like if it is a full pitch coil means the coil span is 180 degree. And if we are short pitching means we are not doing it full pitched. We are not going for 180 degree span, but we are short pitching it. Now here, in terms of machine terminology, if you want to put this particular winding in terms of words, we can say that I have been short pitched. I have short pitched my coil by one slot, right? I have short pitched my coil by one slot. Now, whenever this kind of line comes up in a numerical or whenever you come across this line, okay, you just have to quickly relate to it how much angle it has been short pitched. How will you calculate it? Now if it is one slot, so each slot how much angle it is, so you have to quickly calculate it. So it is coil, each slot I'm having 180 degree plus 6 slots, it is 30. So ideally it should be 180-degree coil span. So then I get a 30-degree slot pitch. So since it is short pitched by 30, my effective coil span will be 180 minus 30, which is 150. So here, that's what your new coil span is, which is 150-degree. So that's how you will understand the terminology. Okay. Now let's get back to our main discussion. Now, by what factor my output voltage will be less in case of short pitch winding? So we call such kind of winding as a short pitch winding. Okay, I'm just trying to write it here, and it will be simple for you to understand. Coil span is equals to 180. This means it is a full pitch coil. Okay. Now the coil is short pitched by some angle. I am calling that angle as a epsilon. Now some turns, and this is full pitch coil. Okay, this is the actual 180-degree. So this is actually your coil span, and this angle I am calling it as a epsilon. Now the new coil span will be 180 minus epsilon. So this is not equal to 180 now, right? Now question is, what is induced voltage in this case? What is the induced voltage? Then definitely it is a short pitch coil. Now, yeah, if it is a full pitch coil, and again, it's same as concentrated and full pitch. If it's a concentrated, it's just addition of all the voltages because they are in the same phase. Now, if it is a full pitch, the angle is 180. They will be the same phase that we will see here. It will be very clear if we always put it in the phases. Okay, full pitch of coil 1 dash. Okay, it is 1 0 0 1 dash, 1 0 and 0 1 dash, these two coils. Okay, now I have two coils, like two coil sides, 0 1 and 0 1, and there will be voltage induced in this side and there will be voltage induced in this side. I am calling that as a E10 and I'm calling it as a E01 dash. Okay, now if I take my phasor E10 in this side, now my E1 dash 0 would be 180 degrees but under opposite polarity. So it will be 180 degrees this side, E1 dash 0. However, this magnitudes will be equal and same magnitude. So since they are 180 degrees and opposite polarity, it will be directions will be opposite. 180-degree phase difference will be there, and they will be coil span 180. That's what I mentioned it here. Now, if I just reverse it, I will just take the inverse of this one. This is this is E10 only, this one, and this is the inverse of E1 dash 0. It will be minus E1 dash 0, this phasor. Same length, of course. Now, the total magnitude will be from here to here, that is E11 dash, this total resultant. So anyhow, the negative is there, but the magnitude, if you see, if I write it in terms of phasors, E11 dash is equals to E10, this one, minus E1 dash 0, this one. Now, if you take the resultant magnitude of E11 dash is equals to, this magnitude will be E, this magnitude will be E, summation of these two will be 2E. So look at this phasor, magnitude will be 2 times of E, that will be 2E. So yeah, as expected, the same in the concentrated winding, we will get a maximum output induced voltage if it's a full pitch coil. Okay, now I am short pitching it. Okay, now short pitch, I have, okay, now this one is 180 minus epsilon. I told you this is epsilon short pitch angle, and this is 1 dash. Okay, now the phasor will not be 180 degrees apart, but it will be 180 minus epsilon apart. So if I try to draw the phasor for this, the E1 dash, E10 will be, this is 10 and it is 1 dash 0. E10 would be in this way. Okay, now tell me how this E1 dash 0 would be. It won't be in this way, but there is an epsilon short pitched. So this is my E1 dash 0 phasor. However, the magnitudes are same. So this angle would be 180 minus epsilon. Right. So now in this, we can easily find the resultant again using some uh, trigonometric and mathematical equations and notations. We can easily find it. Okay. Now I'm just trying to get the reverse of this E10 resultant because I need to find the resultant, right? So this is E10. This is here, and I'm just try to put it here. This particular E1 dash 0 only. I just try to put it here, but in the reverse this way. So this will be minus E1 dash 0. Okay. Angles are again all are same. So if this is this one and this is 180 minus epsilon, this is epsilon. This is minus E1 dash 0. Now what I am interested, this here and this here, I am interested in the resultant. Okay. So this is what resultant is, and I'm calling it as a E11 dash. This is what I want to calculate now. So this is the O, the point, and this is 180 minus epsilon, and this is epsilon. So this will be epsilon, and this is 180 minus epsilon. So that's the angular. So because these two are of same sides, right? E and D. It's like an isosceles triangle. Isosceles sides, two sides are of same. Now, if you see the triangle, let's use some notations. O, A, B. Now let's look at triangle OAB. Now this side is E magnitude and this side is E. Two sides are equal, and here you know this angle is 180 minus epsilon. Now in a triangle, the sum of all three angles is 180, and this is an isosceles triangle. So these two angles will be equal. So then these two sides are equal. Now this is 180 minus epsilon, and this angle is x, and this angle is also x. Now you know the sum of angles. So 180 minus epsilon plus x is equals to 180. So you can know x degrees is equals to epsilon by 2, right? So this angle is epsilon by 2 and this angle is epsilon by 2. I hope this is not that difficult to understand. Okay. Anyway, now we got the angles in all the angles in the triangle AOM. Now I will draw a perpendicular from the O, from here to here. Okay. I'm calling it as a point M. So now I'm interested in calculating the AB. That's the total resultant. What we need is AB. From the phasor, you can see AB is nothing but AM plus BM. Two sides. Now take the individual side AM. Now you take this triangle, this particular uh, AMO triangle. This is a right angle triangle. In this, you know the hypotenuse, which is E10, this one. So let me just draw this right angle triangle here, but that is so confusing there. E10, which is A, this is O, this is M. So this is right angle, and this angle is epsilon by 2, right? This is E10, which is equals to magnitude is equals to E, right? Now AM, now tell me AM, what is this AM side? This is the adjacent side of the epsilon by 2. I'm writing it AM. AM will be equal to magnitude of E10 times cos epsilon by 2, right? So that is AM. If you see similarly BM, BM will be E1 dash 0. Here it is BM will be this hypotenuse, that is E1 dash 0. E1 dash 0 cos same angle epsilon by 2. Right, we got the two sides here, AM and BM, and the resultant will be AB, which is sum of these two. Now AB is equals to, which is resultant E11 dash, will be this plus this. So this, since these are same magnitude, it will be E cos epsilon by 2, and this one will be also E cos epsilon by 2. So the total resultant will be 2 times E cos epsilon by 2, right? Now you got the resultant induced voltage in case of a short pitched winding. So in full pitched winding, what we have got, the total is 2 times E, right? Now in this condition, if you see the short pitched condition, the total resultant voltage will be less than 2E. There is a cos epsilon by 2 factor is being multiplied. Now let's take the ratio of it. Ratio is nothing but our pitch factor. I hope you got that by now. Kp is equals to, again I'm just trying to ratio will be Kp. Kp is resultant voltage when short pitched divided by resultant voltage full pitched. Okay. Now Kp is equals to, what is the resultant we got in short pitched? 2 times E cos epsilon by 2 and 2E. 2E gets cancelled and Kp is cos epsilon by 2. So this is what you get as a pitch factor, right? And what is the formula we got for distribution factor? Let me write that also here. Sine m beta by 2 by m sine beta by 2, right? Sine, yeah. that is distribution factor, and this is the pitch factor. Now, in an AC machine, these two ratios and Kp and Kd are very important because usually all windings are being more or less generally they used to short pitch, or generally they used to like distributed winding because they have their own advantages. So these two ratios will always be important even while winding the machine. So if the windings are distributed as well as short pitched, so the voltage will definitely be reduced by these two factors. So whenever they say if the winding is only short pitched, you will use the pitch factor. If the winding is only distributed, you will use only the distribution factor. But generally, windings will both be distributed as well as short pitched. So in that case, your voltage will be reduced by both factors, Kp and Kd. So that factor is what we call it as a window factor. So sorry, winding factor. We call it as a K with respect to W. So since it's related to winding, short pitch winding and distributed winding, we are calling it as a winding factor, and it's a multiplication of Kp and Kd. This is the amount by which the entire voltage will be reduced, and it's simple. You can calculate it by multiplying Kp and Kd. You will get how much voltage reduction you can observe it. Now, the reason why we are going for short pitched and distribution winding, we already saw it. But there is another added advantage for the short pitched winding and also the distributed winding, because it eliminates a specific harmonics which are unwanted. Now, the advantage of the short pitch winding is, let's say if we want to eliminate the third harmonics. Usually third harmonics are not wanted in the voltage output voltage. Now, if I want to eliminate those harmonics, those third harmonics, it is being wounded in such a way such that we can eliminate the third harmonics. Like if you short pitch the winding by this epsilon, that particular voltage won't be visible. Like I'm just trying to write it here. Like let's say K3P pitch factor. I'm saying cos 3 times epsilon by 2. Now, if I say 3 times epsilon, I have been short pitched by 3 times the epsilon. The reason behind it, I want to eliminate the third harmonics in the system. So in the similar way, if I want to eliminate the fifth harmonics, cos 5 epsilon by 2. So it's another advantage of short pitching the windings and short pitching distributed windings also. And yeah, that's how the advantages are. Now, with this basic understanding, like how the windings are being wound and why the windings are being wound in such a way, why should we go for distributed and why should we go for short pitched winding? Because we clearly saw that full pitch and concentrated winding are giving the maximum voltage outputs, but still the reason behind choosing this distributed and short pitched windings are clearly understood. I hope by now. Now let's try to let before doing that. Let me just write all the formulas we have got it till now. Now, yeah, usually we call M. We call it as a slots per pole per phase. We gave this notation as M here, and distribution factor we got sine m beta by 2 by m sine beta by 2. Here also, if you see, like they're saying that if they are trying to eliminate the third harmonics and they're trying to asking you the distribution factor, this beta will be split by 3 times, 3 beta, third harmonics. If it is fifth harmonics, it will be 5 beta. It's not dependent on M. M is different. M is this slots per pole per phase. Now, apart from M, you have to make the beta multiple of that much times. And pitch factor is equals to cos epsilon by 2. Now, in this K and D, N is nothing but the harmonics I want to eliminate. Sine m n beta by 2 and sine n beta by 2. In the same way, Kp also, Knp, I want to eliminate nth harmonic cos n epsilon by 2. That's it. Did we miss any other formula? Okay, one more formula it will be useful is flux per pole. Flux per pole is if we know the flux density V average flux density per pole multiplied by the area of the that complete pole shoe area of the pole, then you can calculate the average flux density per pole multiplied by A. This is Weber per meter square, and this is in meter square, and this will give you the Weber. This is simple formulas. We will be using all these formulas now in the your assignment questions model. So I think it will be easy for you to relate it. So I request everyone to take a pen, paper, and also calculator with you. We will solve these problems together, and you will also tell me if I go wrong anywhere, or if I do any mistake, you will be there to correct me. So I request everyone to solve the questions with me. So yeah, we have a question here, and they are asking some follow-up questions on it. Let's see what the data they have given, what the data is being provided to us, and what we have been asked. A six-pole machine, okay, a three-phase six-pole 50 hertz generator is having an active length of zero point 0.4 meter and a diameter of 0.4 meter and the 54 slots, 60-degree phase spread, double layer winding. Oh, this we haven't discussed it, but I'm sure you know like what is a double layer winding and what is a single layer winding. So nothing like if it's a, let's say I'm trying to place one coil here, and this goes like that, and it comes like this way, and this is right. Each coil have two turns. So I mean turns means coil sides. So this is one coil side and this is another coil side. Turns, however, there could be many turns for each coil there. Now this is overhang and this is one side. Now this is a single layer winding. In a single layer winding, layer means in each slot there is only one layer. This is coil 1A. This is 1B. So two coil sides will make a coil 1. Okay. Now if you see, only one coil 1 is taking two slots to complete this entire coil. So that is single layer winding. In single layers winding, one coil will have two slots. So two slots will be occupied by only one coil. Now let's say I will go for a double layer winding. If it is a double layer winding, I will place one coil here and return here, and I will place another coil on top of it, double layer. So another coil will go, another coil will come back. Now in this case, these two slots accommodated how many coils? Two coils, right? This is coil side of coil 1, coil sides of coil 2. So if it is a double layer winding, two slots can accommodate two coils. If it is single layer winding, two slots can accommodate only one coil. No, one coil, two slots, two coils, two slots. So whatever you have to remember is if it's a double layer winding, number of coils is equals to number of slots. So here we have a double layer winding and they gave 54 slots. So how many coils we have? 54 coils. That's it. Okay. Now we have to assume the air gap flux density to be sinusoidal. It's a sinusoidal flux density with a maximum B. We are given with maximum B as a 0.8 Tesla. Okay. Okay. Now we have coils have a 4 turns each. Okay. Now if you see this particular coil, we have 4 turns each. Turns means, okay, I started here. This is one coil side and this is one turn. It is not completed yet. It has 4 turns. Second turn. third turn, and fourth turn. Then only it will get completed. So each coil has a 4 turns each. And also we are given that it is short corded by one slot. So short corded, the another word is the short pitched. So okay, that also another information. If it is one slot and there is another slot, so this is one slot epsilon. So this is also information they have given. Okay, I think we have all the information we need, and now we can easily calculate whatever they are asking. So let's just write slots is equals to 54 and poles is equals to 6 pole. Now phases is equals to 3 phase and F frequency is 50 hertz and L 0.4 meter, D 0.4 meter and 60-degree phase spread. Phase spread means how much angle each phase is taking. Here it is 3 phase. Each phase is spreading across 60 degrees of the plane. So that's this, and it is a double layer winding. And anything we missed? So yeah, B is equals to 0.8 Tesla, and turns per coil is equals to 4 turns, and it's a short pitched by one slot. So that we have mentioned it here. Okay, now the first question is slot pitch beta in electrical degrees. So I think it's very simple to calculate the slot pitch if you know the number of slots and also the total spread. Okay, now this is the machine and this is 360-degree mechanical, and total number of slots it is spread. How many slots? We have 54 slots. So 54 slots are spread across 360 degree. Now my beta will be 360 divided by 54. You have to keep in mind this is mechanical beta. Now what is 360 by 54? Can someone calculate it? I'm also calculating here. So it is 360 divided by 54. It's a 6.66 degree, 6.66 degree mechanical, but the question asked is in the electrical degree. Now if I want to get electrical, I will multiply mechanical by pole pairs. How many pole my machine is? It's a 6 pole machine. Now 6.66 multiplied by 6 by 2. So multiply it with by 3. Now I got exactly 20-degree beta electrical. So it means that each slot is having a 20-degree spread like between each slot. That's what it means, beta slot pitch. Each slot is having a 20-degree pitch between those two. Okay. Now the second question is the rated speed in RPM. RPM means usually people represent in N, that is RPM. Omega means radians per second, and if it's a frequency, it's in a hertz, or you call it as cycles per second. So omega we have 2 pi f, and f is cycles per second. If you multiply it by 2 pi, you will get this radians per second. And if you call it in RPM, rotations per minute, you will have to read a 120 f by p, right? This is nothing but this one. Okay, now they are asking it in the RPM, and the speed in RPM is equals to rated speed 120 f by p. So it's a 50 hertz machine, 6 pole machine, and it will be 1000 RPM. It's a very straightforward question. Now the third question is flux per pole, flux in milliweber. Now as we know, the formula for flux per pole is equals to B multiplied area per pole. Now this B, we were given some information about the maximum flux. But usually here we don't take the maximum. We have to read the average of this sinusoidal flux. So we got the this one. This is maximum is 0.8 Tesla. We need to get the average of this one. So average of sinusoidal will be, of course, it's symmetrical. It will be zero. We need to take the integral of this flux density. So we know usually if there is a maximum quantity Vm, it's RMS like will be over sinusoidal will be 2 Vm by pi. Right, you remember that, right? That's the magnitude of the average quantity. So here we know the B max, and we need to have the average flux density. It will be B max 2 B max by pi. Usually it comes when you integrate it over the cycle in which it is existing. If you integrate it over the flux density, you will get the B max by pi by 2. It is 2 B max by pi. 2 B max by pi. Yeah, if you need to calculate the pole shoe area, like you have like this, and you will have the shoe, and they gave you the diameter, and this is the length, and what is the area? Pi d L, right? So that's the area of the pole shoe. Two times B max. Hello. Mute. Yeah, thank you. This is pi dl, and yeah, you just substitute the values. Pi get cancelled at 2 times of B max. How much B max they have given? 0.8 Tesla, and diameter is zero point 0.4 multiplied by length 0.4. This is entirely per pole, flux per pole we are calculating. So please calculate 2 times 0.8 multiplied by 0.4. Okay, 2 times 2 times 0.8 divided by 0.4. Okay. L and 2p. Okay, per pole divided by per pole. So what I got is 0.256 divided by pole. How many poles my machine is? It's a 6-pole machine. It's divided by 6 pole. So what I got here is I'm writing it here 0.04266. It is the Weber per pole. So they asked the question it is the milliweber. So it will be 42.66 milliweber. Yeah, there is another derivation for the getting the flux per pole. I want you all to go through the derivation. I will give you the formula, but you should try that how you got that before next week. It will be useful for you. It's a pretty big derivation. I'm not solving it now. We don't have time for that, but I'm just giving you the idea. Like if you can integrate the flux density over the its period, and you will get the flux per pole. It is integral minus pi to pi. We are trying to pi per pole, right? Per pole. B peak cos of poles theta r multiplied by L r dr. L r d theta r. Yeah. So this is another formula. If you can integrate it, and if you solve it, this is the formula. You will get this at a particular derivation, and you can just substitute it. Even if you just integrate it over here, and integrate of course it will be sine, and it will be poles by 2, and if you divide it by 8, and you will get 2 by pole, and it will be 2 times substituting the limits pi by pole and minus pi by pole. It will be 2 times b peak multiplied by L into R. So if you see, if it is 2 times of R will be D, then 2 by pole B peak L into D. So that's what we also got before, right? In the both ways, you will get the same thing only. So yeah, that's how you can calculate the flux per pole. Simple formula is flux is equals to B into A, where B is the average flux density. Average will be B max by 2 by pi multiplied by area pi dl. So that will be very simpler. And if we solve, you get getting with the 42.66 milliweber. Now let's look at the pitch factor. Okay, we will apply our formulas whatever we have derived in this particular session. And what is the formula for pitch factor we have calculated? Pitch factor is equals to cos epsilon by 2, right? Now since it is short pitched by one slot, how many slot? One slot. Now epsilon is equals to 1 times the beta. Each slot will have a beta. So one slot is 1 beta, that is 20 degrees here. Now Kp will be cos 20 by 2 cos 10. Okay, what's cos 10? Someone tell me what the cos 10 is. Cos 10 is 0.9848. 0.9848. So you can relate it now, right? Like if it's a pitch factor, if you are short pitching by one slot, 0.98 factor will be multiplied to the voltage. So it's the voltage will be 0.98 times of voltage, which will be reduced by this particular factor. That is the pitch factor. Now the next one is, if they were third harmonics, what would have been the pitch factor for third harmonics? Okay, now they are asking us the K3P. K3P will be cos 3 epsilon by 2. So epsilon we already calculated 3 times 20. That's right, 20 by 2. So it's cos 60 by 2. So cos 30, how much is cos 30? 0.866, right? So that's how, if you want to eliminate the third harmonics, you can short pitch by this much factor so that you can eliminate the third harmonics in it. Now the next question is M. We already calculated this M. M is equals to slots per pole per phase. How much slots we have? 54 slots per pole. It's a 6-pole machine divided by phase, 3-phase machine. So 54 by 18, it's a 3. So M is a 3. Now, okay, everyone please calculate the distribution factor with me. So what is the formula for distribution factor? Sine M beta by 2 M sine beta by 2. So M we got 3 and beta is 20 degrees. Let's calculate it. 60 by 2, 3 sine 20 by 2. Okay, please calculate it with me. Let's see. So sine 30 divided by 3 sine 10. Okay, 0.9597. 0.9597. Okay, this is the factor by which our voltage will be reduced if it's a distributed winding. If it's a full pitch wind, short pitch by one slot, we got 0.9848. If it's a distributed, it will be 0.9597. Again, if there were third harmonics, what would have been the distribution factor for third harmonics? 3b sine m 3 beta by 2. Don't confuse m and 3. 3 will be there and m will also be there. M sine 3 beta by 2. So you calculate it with me. So what is m here? M we have 3 and we have again a 3. 3 sine 3 beta by 2. So it's sine 90 divided by 3 sine 30. So 1 by someone tell me what is the answer here. Sine 90 is 1 divided by 3 sine 30. How much you got? 1 divided by 1 divided by 3 sine 30. 0.666. Okay. The answer for this 0.666. Some factor. If it's a third harmonic distribution factor. So number of coils. How many are coils here? So we have the slot information. We have 54 slots, and we already know it's a double layer winding. Now it's a double layer winding. We already talked about it. If it's a double layer winding, two slots will accommodate two coils. So if it's a double layer winding, number of slots will be equal to number of coils. So number of coils is equals to number of slots is equals to 54. And yeah, the last question for today is the RMS value of the EMF generated per coil group. Now that's important. The coil group is important. Like coil group means how many coils are there per pole per phase. Now how much is the M here? That is a 3. So if it's a there are 3 coil groups we have, because each coil have how many coils per pole per phase. So coils are equal to slots here. So how many slots per pole per phase? There are 3 slots per pole per phase. The coil groups will also be there are 3 coil groups per pole per phase. Now, what is the formula for RMS voltage of the EMF formula? It's a very standard formula. Root 2 pi Kp Kd phi ft. So they are asking it for the coil group. So these terms we have to take care. That should be for the coil group, and rest all factors we have calculated per pole frequency and all. So root 2 times pi Kp. How much is Kp we got? Kp we got 0.9848. Kd we got 0.959. Flux per pole is 40. How much we got? 42.66 milliweber. 42.66 10 power minus 3 multiplied by 50 hertz. And turns. In the question, it was given how many turns per each coil. Coil have 4 turns each. One second. Okay. Coil has 3 turns each. So somehow okay. So 4 turns each, and we have 3 coil per groups. So 4 times 3, there are 12 turns per coil group. Now it's just a multiplication. Root 2 times pi multiplied by 0.9848. You can calculate, or I will also calculate quickly. Root 2 14 multiplied by pi multiplied by 0.9848 multiplied by 0.959 multiplied by 42.66 milliweber, 42.66 milliweber multiplied by 12. So how much you got? Okay, you just multiply it and you can note down the value. Yeah, that's how 55 into divided by 12 multiplied by. Okay, so I whatever it is, you do 2 times pi, it's just a straight multiplication. You note down the value, but the important thing is you have to understand the terms here. Why KP KD has come into picture? Because KP KD, if you see, I am directly multiplying it with the EMF generated. So this is a winding factor we are multiplying with. Because of my short pitch winding, because of my distributed winding, these factor times my entire voltage will be reduced, and that's how everything rest we have calculated. And so yeah, let's have a quick summary of uh, so that's all for today, and let's have a quick summary of what we have discussed. We started with the winding terminology, which are important in while we are before discussing a deep three-phase winding how scheme and all. It's a concentrated winding and distributed winding, and from those discussions, we actually calculated, like understood what exactly is a distribution factor, what is exactly is a winding factor, and all. Uh, then pitch factor, distribution factor, and we saw the resultant voltages and how they are being affected with the different magnitudes of resultant voltages based on the kind of winding. And then we saw the derivations with detailed derivations for the resultant voltages in both distributed and concentrated that resulted in a distribution factor. And then we discussed about pitch factor, what exactly is a short pitch, and what how it is the significance in the this particular factors, and the resultant derivations and the detailed derivations. I hope you have understood this. It's a very pretty straightforward derivation. And then we derived the formulas for Kp and Kd, and we discussed the significance of it and how we can eliminate that particular harmonics using these distribution factors, and then basic formulas, and then we started solving the numericals. And yeah, so I hope you have understood today's discussion. And if you have any doubts, please do ask. And I also suggest there are two other TAs who are teaching along by my side the same course and same concepts. But we have divided whatever concepts we'll be teaching, and yeah, I urge you to also attend those sessions as well, because it's a pretty large concepts to cover in a single session. So we are trying to cover all the concepts and giving you in a detailed manner. So I suggest you also attend the rest of the two sessions and interact with the TAs, understand the concepts more clearly, and it will help you in solving the assignments. Not only just assignments, understanding the concept altogether, which will even help you in the any other competitive exams you are going to attend. So that's all from my side together. If you have any doubts in today's session, please do ask me. If I'm not able to answer, I will get back to you next week. And if I can discuss right away, we can also discuss it. Someone type a text. Yeah, Mr. Shailesh. Thank you. Thank you. Okay. Uh, if there are no doubts, we will meet next week, same time, 6 to 8, and we will discuss more concepts in the electrical machines. Thank you all. Thank you for joining, and I'll see you next week. Thank you.